Observe this one. D3, how many unpaired electrons? 3. Color is violet. If electronic configuration is D7, D7, number of unpaired electrons I am saying. D7. Number of unpaired electrons again 3 only, na? Now observe the color for D7. D7 means, can we take cobalt plus 2? Color is pink. Correct? Now observe here. D5, pink. D5, yellow. Are you able to understand? Both have same number of unpaired electrons, but based upon the size of ion, right? If size based upon the size of ion, when water molecules are surrounding it, water is considered as ligand. So based upon the interaction between ligand and settlement ion, even though if they have same number of unpaired electrons, color may change. Is it clear? It depends upon metal and ligand interactions. Any questions in it? No. One more thing. What is the oxygen state of chromium in K2Cr2O7? +6. When chromium is in +6 state, how many d electrons? Where chromium is 24, man. Configuration 4s2, 3d, sorry, 4s1, 3d5, chromium. D6 means how many unpaired electrons? If there are no unpaired electrons, the color should be, it should be colorless. Correct? But such complexes are colored due to ligand to metal charge transfer. Right? In some cases, even though there are no unpaired electrons in d orbitals, they show color because of ligand to metal charge transfer. So I am writing that point. In case of K2Cr2O7, K2CrO4, KMnO4. What is the color of K2Cr2O7? Orange. What about color of K2CrO4? Yellow. What is color of KMnO4? Purple. What is color of K2MnO4? Green. But I have one unpaired electron. Check. I have one unpaired electron, and that's why I'm not taking it. Right? So here +6, +6, +7. No, +7. No unpaired electrons, but they are showing color. In these cases, color is due to ligand to metal charge transfer. Any questions are in this? Right? What is the hybridization? What is the hybridization of K2Cr2O7? K2CrO4, KMnO4. All are tetrahedral molecules. And if you take K2Cr2O7, observe this. K plus, here also K plus. Is it K2Cr2O7 or not? Right? +6 state, +6 state. Both are tetrahedral. Hybridization of chromium is D3s. Right? K2CrO4 also same. Is it K2CrO4 or not? Respond. Same way KMnO4. Is it KMnO4 or not? So all of them are tetrahedral molecules and all have hybridization of T3s. And all of them are colored due to ligand to metal charge transfer, right? So here we are talking about aqueous solutions, man. Here we are talking about aqueous solutions. Aqueous solutions means I am considering water as a ligand. Means what is the meaning of it? Scandium is surrounded by water molecules. Then what is its color? So can I write as Sc plus 3 aqueous, titanium plus 4 aqueous, Zn plus 2 aqueous. All these are colorless. Clear? Next one, sir. I am talking about vanadium. Vanadium plus 2, vanadium plus 3, vanadium plus 4. In different oxygen states, number of electrons in case of vanadium plus 2. Scandium, titanium, vanadium. Right? 23 means 4s2, 3d3. Plus 2 state. D3. Here D2. Here D1. If it is vanadium plus 5, colorless. Response, sir. No. As number of unpaired electrons in d orbital changes, color also changes. What about vanadium plus 2 color? Plus 2 color, violet. Vanadium plus 3 color, green. Vanadium plus 4 color. Vanadium plus 4 color, blue. Right? Next. Cobalt plus 2, cobalt plus 3. Iron, cobalt. Cobalt means D7. Right? Response, sir. So can I write as D7 here and D6 here? Correct? And color. This is blue or pink? Cobalt plus 2, pink. Cobalt plus 3, blue. Same way, iron. Iron plus 2, iron plus 3. Iron plus 2 is D6. Here it is D5. Color. Green, yellow. Any other element showing variable oxygen states? Chromium. Chromium also there? Chromium plus 2, chromium plus 3. In chromium plus 2, this one, D. 4s1, 3d5. Plus 2 means D4. Correct or not? Plus 3 means D3. Color. Plus 2 is blue, plus 3 is violet. Is there any other species having different oxygen states? Manganese, huh? Manganese plus 2 plus 3, huh? Manganese plus 2, manganese plus 3. In case of manganese plus 2, D5 plus 3, D4. Here, manganese plus 2 color, pink or buff colored. Manganese plus 3, violet. Is there any other element showing different oxygen states? Titanium, huh? Titanium plus 3. Titanium plus 3. Plus 2 also there. Titanium plus 3 plus 4. Titanium plus 3. D. That is scandium, titanium, D2. Plus 3 means D1. Plus 4 means T0. Now color +3, purple, +4, colorless. Response, sir. Is there any other element showing different oxidation states? No. Now, this is the different elements showing different oxidation states. Now I am talking about ions showing same color. I am writing ions showing same color. Now identify the ions which shows same color, violet. Same violet color. Right? Here. Vanadium +2. Chromium +3. Manganese. Copper blue color. Cobalt also not given, huh? Cobalt given, huh? Copper +1 +2, huh? Do they give copper +1? No, no. So I am not writing it. I am giving elements showing variable oxygen states, different colors. Right. Vanadium +2, chromium +3, manganese +3. All these show violet. Next one. Cobalt +2. So cobalt +2, manganese +2. Pink, huh? Both shows pink. Any other? Vanadium +4, blue color. Vanadium +4, copper +2, chromium +2, cobalt also. All these shows blue color. Next. Vanadium +2. Violet, violet already written, man. +3 green. Vanadium +3. Iron +2. Nickel +2. All these three shows green color. Any other? Yellow. Iron +3. Yellow. Iron +3. Any other? Titanium. Purple. Any other? Right? So you need to remember the ions which are showing same color, or we need to remember element in a different oxidation state showing different colors. Any questions, sir? So we are done with color of ions. Next one, magnetic properties. Next one, magnetic moment. Indicate a symbol mu, can be written as mu equal to, if it is spin only magnetic moment. If it is a spin only magnetic moment, then what we will write? Mu equal to root of n into n plus 2 mu b. Correct, sir? Means Bohr magneton. Or this can also be written as 4s into s plus 1 under root. What is one Bohr magneton? EH upon 4 pi m, which is equal to 9.27 into 10 power minus 24 joule per Tesla. Right? Any other? Then orbital, this is spin only magnetic moment. Then what about orbital magnetic moment? Orbital magnetic moment. Stop talking. What you will write? Capital L equal to root of L into, yes, sir. L into L plus 2 1 L into L plus 1 Bohr magneton. What is Z component of orbital magnetic moment? What is Z component of orbital magnetic moment? In structure of atom, we have seen all these points, man. What is Z component of orbital magnetic moment? Root of L into L plus 1 into cos theta. Say something. 1 minute, man. Structure of atom, na? While we are discussing about quantum numbers, all these points we have seen. Listen. I'll stop talking, man. This is one is orbital angular moment, root of L into L plus 1 H cross. If it is orbital magnetic moment, wait, where is it? Here. Orbital magnetic moment, Z component, right? Then what you got? Root of L into L plus 1 into H cross into cos theta, right? Z component of orbital. If I write H cross, it is called angular moment. If I remove H cross, then it is called magnetic moment. Respond. Now, there is spin only magnetic moment, not there. Huh? Right? You have not written magnetic moments. This is orbit angular moment. This is orbital angular moment, right? This is Z component of orbital. Oh, we should not write magnetic, right? Orbital angular moment because I used H cross, right? If I remove that H cross and if I write mu B, Bohr magneton, then it is called magnetic. Clear? Understood or not? If I add both, what you will get? Let me write it as capital S. Let me write this as capital L. Sum of capital L plus capital S is called total magnetic moment. We write as Z. Z is equal to L plus S. Say something, right? Where Z is called total magnetic moment, right? Or we also write Z is equal to root of 4S into S plus 1 plus L into L plus 1, right? Mu B, right? Magnetic moments of species is measured experimentally by using one balance called Guay balance, right? So what do you mean by Guay balance? Guay balance is used to measure magnetic moment. Continuously you are talking, man. Third bench. Third bench or fourth bench? Fourth bench. Here we kept three conditions. What are they? Right? MA and what is MA? This is mass of the substance in absence of magnetic field. Another one? MB. Mass in presence of magnetic field. Now, if the condition MA greater than MB, what happened? In absence of magnetic field, its mass is more than presence. Means in presence, its mass is less, means in presence of magnet, it is repelled. So it is diamagnetic substance. Next one, if MA less than MB, then
magnetic substance.
Paramagnetic. If MA equal to MB, non-magnetic or anti-ferro. If MA is far less than MB, then it is ferro. All right, because in case of ferromagnetic field, they will attract very strongly. If they attract very strongly, what happens to the mass? I need to keep more mass to weigh it. Clear? To balance it. Understood? This is about magnetic moments. Any questions, sir? Say something.
No,
Next.
sir.
Stability of. So we are done with this color of ions we have done. This one we have seen magnetic properties. So in this magnetic properties, this is the table. Based upon number of unpaired electrons, this is calculated. This is experimentally observed. In few cases, there is difference between experimentally observed and theoretically calculated. That difference is because of orbital magnetic moment. Because here we are using Spinozzi magnetic moment to calculate. But here experimental value, we are getting some difference. The difference is because of orbital magnetic moment. Clear? Any questions in this? So magnetic moment table is over. Here they gave some, oh, they have not given that value. Huh? Okay, leave it. Here they give ferromagnetic substances strongly attracted. Same points we have discussed in solid state chapter. Para, dia. What is CrO2? What is CrO2? CrO2. This is what, man? Huh? Observe CrO2 where it is. That's what we are discussing now. What are ferromagnetic substances? If I keep an external magnet, all domains are aligned to same direction permanently, right? And they attract external magnets strongly. Even after removing external magnet, they themselves behave as a magnet, right? Example, iron, cobalt, nickel, gadolinium, CrO2. Response, sir? No. Diamagnetic. All are paired. So in presence of external magnet, it will weakly repel external magnet. Example, benzene, NaCl, water. Correct? Next, paramagnetic. All domains are random. The moment you bring an external magnet, all are aligned in one direction. If I remove it, they will go back to normal. They are called as, and they weakly attract external magnet. Example of paramagnetic, anything which is having unpaired electron. Can I say O2? O2 is paramagnetic. Cu plus 2, one unpaired electron. Fe plus 3, Cr plus 3, etc. Response, sir. What is color of Fe plus 3? Yellow. Chromium plus 3. Just now we have seen chromium plus 3 color. Violet. Copper plus 2. Blue. Now, antiferro. Example, MnO. Correct? Now see here. Similar to ferromagnetic, but all oppositely oriented and cancel each other's magnetic moment. That is antiferro. So what happens to net moment? 0. Means it is similar to non-magnetic. Ferri. Net moment is not negligible. Right? So this Ferri. Fe3O4, MgFe2O4, ZnFe2O4. Unequal number of alignments in opposite direction, weakly attracted by magnet. Means it is similar to paramagnetic. On heating, all of them will convert into paramagnetic. The temperature at which they lose their magnetic properties is called Curie temperature. Clear? Over. This is about magnetic properties. We studied that in solid state. So this part is over. Now, above this part, we need to study about this is chemical reactivity and E0 values. Already we have studied it. Are strong oxidizing agents, weak oxidizing, strong reducing agent. Those points already we have studied, right? We need to see these things, oxides and fluorides. These two we need to study, right? So trends in stability of higher oxygen state. This part we need to study. First, we are studying about oxides. In case of P block, higher oxidation states are observed in fluorides, but in case of D block, higher oxidation states are observed in oxides. So I'm writing it. In a D block, higher oxidation states are observed in oxides, whereas in P block, higher oxidation states are observed in fluorides. Example, if you take iodine, I2O5 or I4O10 is the maximum oxidation state shown by iodine in oxides, whereas in fluorides it shows IF7. So here it is +7, but here it is +5. Right? Now, here if you consider example manganese. Manganese shows Mn2O7 and MnFO4. Means in fluorides, it shows maximum of +4, but in oxides, +7. Why you are getting higher oxidation states among oxides? Because of ability of oxygen to form multiple bonds. So here reason is due to their ability to form multiple bonds. Therefore, you will get higher oxidation states are possible. Example. Observe this table. Observe this table. Here scandium +3 state and based upon oxygen states only. +3, titanium +2, +3, +4, vanadium +2, +3, +4, +5. Once open that oxidation states. In oxidation states also we have seen the same now. Scandium shows +3 state. Correct? Then vanadium shows +2, +3, +4. Correct? Vanadium +2, +3, +4, +5. Chromium +2, +3, +4, +5, so not +5, +6. Manganese up to +7. But iron shows maximum up to +3. Right? Only in alkaline medium +6. But which undergoes, which disproportionates to form Fe2O3 and gold. Now, cobalt +2, +3. Nickel +2, copper +1, +2, zinc +2, stable oxidation state. And the same thing they have written in terms of oxygen. Is it clear? But here, instead of writing this, we will separate them into acidic, basic, amphoteric. Right? So instead of writing this, we'll write that in this way. Based upon oxidation states, they exhibit acidic, basic, and amphoteric nature. Basic nature is observed in lower oxidation states. Acidic nature is observed in higher oxidation states. Right? Acidic nature is observed in higher oxidation state. Basic nature is observed in lower oxidation states. Now observe this case. Acidic oxides. Easy to remember. V2O5, CrO3, Mn2O7. Here manganese is in +7. Here it is +6. Here it is +5. Right? These three are acidic oxides, in which V2O5 is, in case of V2O5, one specialty, one exception. Actually, in some books, they will write V2O5 as amphoteric, but acidic characters dominate. Right? Based upon the reaction, it shows more acidic characters. That's why instead of writing amphoteric, we are writing that in acidic oxide list. Right? Actually, it is amphoteric, but acidic properties are more. Is it easy to remember acidic oxides among all of them? Next, amphoteric oxides. Oxides of beryllium, zinc, aluminium, gallium, germanium, tin, lead, arsenic. These oxides are amphoteric. What are amphoteric? They can react with acids as well as bases. So they can react with acids as well as bases. Karthik Sabarish. Why I wrote them in this way? S block. In a D block, zinc. In a P block, aluminium, gallium, carbon family, germanium, tin, lead, nitrogen family, arsenic. That's why I have written that in this way. Right? Next. But we are discussing about amphoteric and basic acidic oxides of D block only, na? Right? So zinc is amphoteric. Correct? In addition to zinc, other elements in different oxidation states are also amphoteric. So I am writing amphoteric oxides of D block in different oxidation states. Titanium, chromium, CrO2, Cr2O3, manganese, MnO2, Mn2O3, Mn3O4. Over. These are amphoteric oxides. Remaining all oxides are basic. Now once open your target booklet and check that oxides list. Zinc oxide is amphoteric. Already I told, no? Zinc oxide is amphoteric. Right? Other than this, I am showing remaining. Right? Responser. These three are acidic. These six are amphoteric. Remaining all are basic. So in the list, what are the other oxides given? Basic oxides. First they gave scandium or not? Respond. Scandium oxide given or not? After scandium, titanium. Titanium, I am taking TiO, Ti2O3. Scandium plus 3 state, titanium plus 2 plus 3 state. I have not written titanium plus 4. Scandium, man. 4s2 3d1. Correct? Titanium 4s2 3d2. So in which I wrote plus 2 state and I wrote plus 3 state. Why I am not writing plus 4 state? Plus 4 state is amphoteric. Respond. So that's why I wrote only these two. Right? Next, scandium, titanium, vanadium. Vanadium, I am writing VO plus 2 state. V2O3 plus 3 state. VO2, or I will write V2O4 plus 4 state. All are basic. I am not writing V2O5. What? Here. I am not writing V2O5 because V2O5 is in acidic list. Correct? V2O5, man. Acidic properties are more. Amphoteric acidic properties are more. So I am not writing that. Next, after vanadium, chromium, I am writing CrO plus 2. I am not writing Cr2O3, CrO2. And I am not writing CrO3. Are you able to understand? Then manganese, MnO plus 2 state I wrote. Here plus 3 state. Here plus 4 state. Here plus 7 state. Right? Lower oxygen state is basic. In between, amphoteric. Higher oxygen state, acidic. Respond, sir. Next, iron, FeO, chromium, CrO, sorry, cobalt, COO. 1 minute, sir. It is not working. Just a minute. Cobalt oxide, nickel oxide, copper oxide, and I am not writing zinc oxide. I am not writing zinc oxide, sir, because I will write zinc oxide here, right? Respond. Correct or not? In case of copper, I am underlining Cu2O. Slightly acidic. Right? So we are done with acidic, basic, amphoteric oxides of C block. Is it clear? If you observe carefully, lower oxygen states are basic, higher oxygen states are acidic. Instead of remembering all these things, simply remember these 3 and these 6. Right? V2O5, Cr2O3, sorry, CrO3, Mn2O7. Acidic, in which V2O5. Amphoteric but acidic character more. Now amphoteric, TiO2, chromium, CrO2, Cr2O3. Plus 4, plus 3, plus 4. Then here, plus 4, plus 3. This is mixed oxide. This is mixed oxide, sir. Add MnO, and Mn2O3. Mixed oxide. Are you able to understand? Then zinc oxide. Right? Zinc oxide already you know. So remove that. Remaining 6 you need to remember. Clear? MnO2, Mn2O3, Mn3O4, CrO2, Cr2O3, TiO2. These are amphoteric. Remaining all are basic. Any queries, sir, regarding this? Online. Do you have any queries in this?
No, sir.
What are mixed oxides? Yes, sir. What are mixed oxides? Just now we have seen, man. 2 different oxygen states. Example, I am taking Fe3O4. Right? What we call it as magnetic oxide? Yes, sir. Can I call it as magnetic oxide? This is combination of FeO and Fe2O3. Yes, sir. Correct only, ore. Right? That's why it is called magnetite or magnetic oxide. Next, I am taking Mn3O4. It is also mixture of MnO 2 moles and MnO2. Balanced. 2 moles of MnO and 1 mole of MnO2. Right. Next one, cobalt. CO3O4. This is also combination of cobalt oxide plus CO2O3. Check. Respond. Done or not? Any other queries? Any other queries? No. Already we have seen these things. Color of MnO4, CrO4, INS, Cr2O7. All these things we have already seen. And they have no unpaired electrons, but they are colored due to ligand to metal charge transfer. Whenever they have unpaired electrons in d orbitals, they are also colored. Reason, if we have unpaired electrons in d orbitals, they are also colored due to series. We call it as DD transition. If we take d orbitals, how many d orbitals are there? 5 now. What are they? dxy, dyz, dzx, dx square minus y square, dz square. Right? All we call them as degenerate orbitals. Orbitals having same energy. When water approaches it, water acts as a ligand. When ligand approaches along the axis, orbitals which are along the axis will have more energy. Remaining orbitals which are between the axis have lower energy. So, what are the orbitals which are between the axis? dxy, dyz, dzx. Their energy goes down. dx square minus y square, dz square. Their energy goes up. So, this is called splitting. Now, when they get splitted up, if you have one unpaired electron here, D1 configuration, this one unpaired electron by absorbing radiation can jump to higher energy state and come back to ground state by emitting that in the form of radiation. This is the reason it shows color, right? So color is due to DD transition. If we have unpaired electrons, they exhibit color due to DD transition. Instead of this, there may be another possibility also. Instead of splitting in this way, they may split in this way also. T2G can be here, EG can be here. If a T2G here, EG here, we call them as octahedral complexes. Right. This is octahedral complexes. Here we call them as tetrahedral complexes. Instead of writing tetrahedral, don't write this G. Simply write as T2E. Right? Tetrahedral complexes. Similarly, if you have unpaired electrons in f orbitals, they are also colored due to FF transition. Here we call it as DD transition. So if you have unpaired electrons in d orbitals, they exhibit color due to DD transition. If you have unpaired electrons in f orbital, then also they exhibit color due to FF transition. So similarly, FF transition. Any questions, sir? Respond. Do you have any queries in this? Next, one more point, sir. Note. Old JEE advanced question, sir. I think this is given in your NCERT also as this one. How would you account for the increasing oxidizing power of VO2 plus Cr2O72 minus MnO4 minus? Which is stronger oxidizing agent? KMnO4. Better oxidizing agent than K2Cr2O7. Then NaVO2. Respond. Sorry, VO2 plus now. VO2Cl. Right? So compared to this, it is better oxidizing than this. This is due to increasing stability of lower species to which they are reduced. It means, for example, manganese. Here it is in +7. It converts into Mn+2. So as Mn+2 is more stable, this readily converts into +2. Means it loses. It gains electrons more readily because Mn+2 is more stable. Are you able to understand? So why MnO4 minus is better oxidizing agent means its Mn+2 is most stable. That's why it readily converts into that, and here hence it acts as a good oxidizing agent. So I'm writing the same point. Note, very important bit. Old JEE advanced question. MnO4 minus is better oxidizing agent than Cr2O72 minus is better than VO2 plus. So their oxidizing power order. Why they follow this order? Due to increasing stability of their respective lower oxidation states. Which are obtained from them. Lower oxidation states into which they are reduced. Right? Any questions, sir? Any questions in this?
No, sir.
Now, next point, sir, regarding fluorides. Regarding fluorides. Better I will write as regarding halides. This is regarding oxides, no, regarding halides. In NCERT, they gave one table. Observe the table carefully. Regarding halides. Observe this table. I am copying this table as it is. Observe this table carefully, sir. Please. Here they gave titanium X4, titanium X3, titanium X2. On the top, they gave Roman letter 3. Now see this, what is that Roman letter 3 indicates? Fluorine to iodine, means there is no fluorine. So TiF2 doesn't exist. That is the meaning of it. Are you able to understand why TiF2 doesn't exist? Fluorine is a good oxidizing agent. If a fluorine is a good oxidizing agent, it always try to exist in higher oxidation states. No? Or if fluorine is a good oxidizing agent, means it oxidizes titanium to higher oxidation state. Higher oxidation state means it has to be in +4. Are you able to understand? Fluorine is a good fluorine, oxygen. These are good oxidizing agents or not? Of course, to some extent, fluorine also, right? So they exist only in higher oxidation state. That's why fluorides are not possible at lower oxidation states for titanium. Clear? Now observe here symbol 1, X1. Here X1. I am underlining this. This one. This one. What is that one? Fluorine to bromine. There is no iodine. Reason? Iodine is a good reducing agent. So good reducing agent exists in lower oxygen, and a good oxidizing agent will make metal atom to exist in higher oxygen state. In the same way, good reducing agent will make metal to exist in. So that's why vanadium +4 is not possible. Vi4 is not possible. Is it clear? Next. Here all are okay. Observe these two. This also. This. This, this one, this one, these two. These are all exceptional cases. Why I underline VF5? A vanadium +5 state. What is fluorine? Good oxidizing agent. If it is good oxidizing agent, higher oxygen state. So remaining are not capable of bringing vanadium up to +5 state. So only fluorine is able to make it to exist in +5 state. Are you able to understand? Same way chromium. Chromium +5 and +6 only shown by fluorine. Remaining are not there. Are you able to understand? Right? So I am writing that. Higher oxidation states are observed only in fluorides and oxides. Reason? Fluorine and oxygen are good oxidizing agents. In a D block, higher oxygen states are preferred in oxides form. In a P block, higher oxygen states are preferred with fluorides. Already we discussed that point. Clear? So I'm writing the same. Generally, higher oxidation states are stabilized by fluorides and oxides. Reason? Fluorine and oxygen are good oxidizing agents. Respond, sir. Respond. Vanadium V2O5, vanadium VF5, chromium CrO3, chromium CrF6. These are some examples. Clear? Here vanadium is showing +5 state. Here chromium is showing +6 state. So higher oxygen state of vanadium is +5. Higher oxygen state of chromium is +6. So such higher oxygen states are shown by either fluorides or oxides. Any questions? No. Iodides prefer to exist in higher or lower oxygen states? Lower. Reason? Iodine is a reducing agent. So I am writing that point. Next point. Iodides prefer to exist as lower oxidation states. Right? Reason, sir? Next, one more point. In a +2 state, titanium in +2 state, exceptional points I am writing. Titanium in +2 state, only for a +2 state, 3 man, only chlorine, bromine, iodine. There is no fluorine. Because when I take fluorine, titanium prefer to exist in higher oxygen state, +4. Coming to manganese. Now observe manganese. Higher oxygen state of manganese among halides is +4, that to MnF4. Why it is not forming MnF7? Fluorine cannot form multiple bonds, all form single bond. If there are 7 fluorines, every fluorine have 3 lone pair of electrons. If there are 7 fluorines surrounding manganese, all lone pairs will repel each other and hence it will decompose. Clear? That's why it prefer to form maximum of +4. So I'm writing manganese. Manganese exists as fluoride up to +4. But if you take oxides, it can form up to 7. Why it is forming up to +7 in oxides? Oxygen can form multiple bonds. And each manganese is surrounded by 4 oxygens only maximum. Right? Or Mn2O7 na? So I'm writing it as Mn double bond O, double bond O, double bond O, single bond O, manganese. Is it clear? Response, sir. Tetrahedral. Both manganese are having D3S hybridization. Any questions in it? Right? Any questions in it? One more point. If you consider fluorides are generally stabilized by, fluorides are stabilized by, see this. Right. See any point like higher lattice energy? Is there any such statement as higher lattice energy? No, no, 1 minute, 1 minute, stabilize. Just now I have seen somewhere stabilize. Not there. Anyhow, see this point. Fluorides are generally stabilized by 3 points. 1, lattice energy. 2nd, bond enthalpy. 3rd point, higher oxygen states. So fluorides are stabilized by generally 3 points. 1, high lattice energy. 2nd point, bond enthalpy. 3rd point, higher oxygen states. These are 3 points stabilize fluorides. Next point, sir. There is one more exception in case of vanadium. VX41. What is that one? There is no iodine, so I am taking that. So VX4 means can write VI4 doesn't exist. Say something. VI4 doesn't exist. Now here PiF2 doesn't exist. Say correct or not? After that, observe this FeX3. Here also 1. What is that 1? So FeI3 doesn't exist. Reducing agent, but iron is +3 is higher oxygen state. Then CuX2. What is that X2? No bromine iodine. Means CuBr2, CuI2. So I'm writing that point. Cu Br2 CuI2. Next one. CuX3. What is that X3? CuF. All right. Right. Instead of saying doesn't exist, I am writing it as doubtful existence. Yes, sir. Yes, sir. Go. They have doubtful existence. Any questions in this? Sir, you are saying CuI2. But generally, if you see reactions, in those reactions, you will find CuI2. I will show an example. Coordination. CuI2. Generally, CuI2 disproportionates, right? Think somewhere observe, is there anywhere can you find CuI2? Not this one. Here. Observe. Copper on reaction with I minus, it is forming Cu2I2 plus I2, but it is not forming CuI2. Are you able to understand? Right? Same thing they are explaining. What they are saying here. Although vanadium plus 5 is represented only by VF5, because fluorine is good oxidizing agent, that's why vanadium exists in higher oxygen state. The other halides, however, undergo hydrolysis to give oxohalides, particularly vanadium. Another feature of fluorides is their instability in, already we discussed this point, right? Example, VX2. X is chlorine, bromine, iodine, but not fluorine. Correct? And the same applies to CuX. Means CuF doesn't exist. CuF2 exists. On the other hand, all copper 2 halides are known except iodine. Means CuI2 doesn't exist. Reason, iodine is a good reducing agent. It reduces copper plus 2 to plus 1. Right? In this case, copper plus 2 oxidizes I minus 2 I2. Is it clear? So I am writing that reaction as it is. Note. Yes, sir. Yes, sir. Copper plus 2 plus I minus gives rise to what I will write? Cu2I2, correct? Plus I2. So I am writing 4I minus 2 copper plus 2. Response, sir. So in case of iodine, iodide, copper prefer to exist as plus 1. Right? Instead of iodine, if I take water or fluorine or chlorine, then it prefers to exist as plus 2. Right? Observe the same statement. Observe here. However, here copper is in plus 1 state now. However, many copper 1 compounds are unstable in aqueous solutions and readily converts to copper plus 2. They undergo disproportion. Reason, when copper plus 2 is there, when copper plus 2 is surrounded by water, more hydration energy is released and hence it becomes stable. See, the stability of copper plus 2 rather than copper plus 1 aqueous is due to much more negative enthalpy of hydration, right? Which more than compensates its second ionization enthalpy of copper. So to convert copper to copper plus 2, I require ionization enthalpy. Compared to that, its enthalpy of hydration is more negative. That's why in aqueous medium, copper plus 2 is stable, right? In remaining cases, copper can show plus 1 state. Understood? So I am writing the same point. Under note, another point. Copper +1 salts disproportionates. In aqueous solutions. Right? Example I'm writing. 2 copper +1 aqueous gives rise to copper +2 aqueous plus copper. Now, in case of copper +2, its a delta H of hydration is more negative than is 1 minute, sir. Is more negative than its a delta H2. Response, sir. Right? Therefore, copper +2 aqueous is more stable. Respond. Any other questions in this? So this point is over or not? Next point. We need to discuss this one. In case of VFO5, when a fluorine is present, higher oxygen state +5 is there. If instead of fluorine, if you want other halogens, minimum oxygen must be there. Because oxygen is also good oxidizing agent. That's why other halides will react with water to form oxohalides. Right? So I'm writing the same. Another point. Other halides of vanadium. Other halides of vanadium undergo hydrolysis to form, hey, where man? Huh? To form compounds like VOX3. Right, sir. One more point. Please listen. Listen. In case of manganese halides, maximum oxygen state shown by manganese is +4, MnF4. But observe this compound. Here, what is the oxygen state of manganese? +7. But it is also fluoride. Right? Due to presence of oxygen, it is showing. If there is no oxygen, it can show maximum of +4. That's what they are saying. Right? +7 state for manganese is not represented in simple halides, but MnO3F is known. And beyond manganese, no metal has trihalides except FeX3 and COF3. Same point. See this? Beyond manganese, after manganese, what is the maximum oxygen state here? +3. +3. There is no other halide more than +3. Right? Same point we are writing. Manganese O3F +7. Right? Is can be obtained. Right? It can be obtained. One more point. Arey, what is this, man? Huh? Arey, go for break. Now time is 7:45, 7:46. Come back by 7:51. 5 minutes break. All of you go and visit washroom. Take attendance there. Huh? You give your attendance at washroom and come back. Go. Yeah, our batch students are more interested in the smell of ammonia. Okay, urea, uric acid. You don't want to be here. You want to spend time there only, right? Or I will ask them to arrange one board there, ma'am. You can comfortably stand there, having the smell of uric acid of everyone in the campus. Huh? You don't want to come from there to here, right? Right. We are seeing one point, sir. What is it? MnO3F can be obtained. Here we discussed one more point. From NCERT, we have seen one point now. Beyond manganese, right? Iron and cobalt shows only +3 state. Remaining doesn't have even +3 state. Correct or not? Where is that? See. And beyond manganese, no metal has trihalides except cobalt and iron. Beyond manganese, no halides have +3 except FeX3 and cobalt F3. Why I am writing FeX3? FeCl3, FeBr3. But in case of cobalt, CO F3 only. Correct? Here. Understood? Next. This point already, here, this is what we discussed. The ability of fluorides to stabilize higher oxidation states is due to either higher lattice energy or high bond enthalpy. Respond. To form higher covalent compounds. We discussed these 3 points or not? Next, vanadium plus 5, already this is done. This is also done. This is also done. Now coming to this. The ability of oxygen to shift, this is also done. Multiple bonds. Higher oxygen numbers in the oxides coincides with the group number and is attained in scandium to manganese. Beyond group 7, no higher oxides of iron above Fe2O3 are known. Although ferrites, already we discussed this point or not? Right, in the alkaline medium, which is disproportionate to this. Now, besides the oxides, oxocations stabilize vanadium plus 5 state. Besides oxygen, there are oxocations also, means oxygen, minimum one oxygen is necessary to exhibit higher oxygen states. Clear? Already we discussed this point also. All these points are over. Mn2O7 structure also we have seen. Right? All these things are over. After that, this table also over. In this acidic basic amphoteric oxides also over. This exception also we have discussed. Now we need to discuss this is also over based upon E0 reduction potentials, good oxidizing, good reducing agent, and so on. So this is also over. This is also over. Response, sir. Next. This is also over. Much larger third ionization energy of manganese is mainly responsible for this. This also explains why +3 state of manganese is off. That's why manganese +3 they are not bothered, right? Why E0 values of Mn3 to Mn+2 much more positive than chromium +3 to chromium +2 or Fe+3 to Fe+2, right? Say this. Oh, not here, huh? Here. Manganese, iron, cobalt. 1.57, 0.77, 1.97, right? Now read that, what they are saying. Why the value, E0 value of Mn+3, Mn+2 more positive than chromium and iron? They are not comparing cobalt, sir. Actually, cobalt value is more. They are comparing chromium and iron, right? Reason for that is delta H3. Much larger third ionization energy of manganese, where the required change is D5 to D4. Because what they are saying, in +2 state, manganese is having D5 state, whereas in +3 it has to convert into D4. So from D5 to D4, I need to spend more energy because it is half-filled now, more stable, right? Is mainly responsible for this, whether we have taken that point or not. D5, D10. Here. We discussed at that point, man. Mn+2 is in D5 state, right? So better I am writing the same point here again. Same point here again. Now what is it? E0 reduction of Mn plus 3 to Mn plus 2 is more positive than Cr plus 3 to Cr plus 2 and Fe plus 3 to Fe plus 2 is due to high delta H3. Correct? Reason in Mn plus 2, its configuration is D5, whereas in Mn plus 3, D4. Understood? Now coming back. Magnetic, after that, why is the highest oxidation state of a metal exhibited in its oxides are fluorides only? Oxides and fluorides are good oxidizing agents. Which is a stronger reducing agent? Chromium plus 2 or Fe plus 2? Why? Which is a stronger reducing agent? Chromium plus 2 or Fe plus 2? And what is chromium atomic number? Configuration? Right? Now, in case of iron, plus 2 state means D4. Now, iron plus 2 state means D6. Correct? D6 can convert into D5 easily by losing electron. Means it can lose electron easily. Means it is a good. That's what they are saying. Which is stronger reducing agent? Why? Fe plus 2 is a good reducing agent because it can convert into plus 3 readily. Are you able to understand? One more point is also there, man. Comparing this point, sir. Why is chromium plus 2 reducing and Mn plus 3 oxidizing, even though both are having D4 configuration? Yeah, chromium plus 2 is reducing agent. Mn plus 3 is oxidizing agent, even though both are having D4 configuration. Observe this, sir. I'm reading that point. Chromium plus 2 is reducing agent. Manganese plus 3 is oxidizing agent. Configuration here is D4. Here also configuration is D4. Even though both have D4 configuration, this acts as reducing, this as oxidizing. Reason. A reducing agent means it is trying to lose electron. Why it is trying to lose electron means T2GEG. If it converts into T2GEG, say this. If it splits to T2GEG, after losing one electron, this becomes, after losing one electron, it becomes a D3 configuration. When it gets a D3 configuration, what happens? T2G orbital becomes half filled. Therefore, it becomes stable. Now coming to manganese. If it gain electron, it becomes a D5. Respond. If it becomes D5, it becomes half filled. Are you able to understand? Right? If it gain electron, it forms D5. D5 means all d orbitals having one unpaired electron. Means above 2, below 3, all have one unpaired electron. Right? Now see the reason what they have given. Chromium plus 2 is reducing as its configuration changes from D4 to D3. In a D3, the later means in D3, having a half filled T2G. Right? On the other hand, the change of Mn plus 3 to Mn plus 2 results in D5 configuration, which has extra stability. Are you able to understand? Right? Now, why chromium plus 2 is reducing? Because when D4 converts to D3. In a D3, it will get T2G3 configuration, correct? Which is half filled. Respond, sir. When a D4 converts to D5, here half filled. Here T2G is half filled, that's why it acts as reducing. Here D5 itself is half filled, that's why it is oxidizing. Clear? Any questions, sir? Respond, respond. Observe this. Fe plus 2, chromium plus 2, which is better reducing agent. Or if reduction potential is more negative, or from left to right, it is becoming more negative or less negative. Or here it is positive, that's right. So if reduction potential is more negative, it undergoes oxidation. Means it is a good reducing agent. Means Fe plus 2, chromium plus 2, which is good reducing agent. Reason. Just now we have seen, man. T2G3. Just now we have seen because of T2G3, right? Fe plus 2 is also good reducing agent. Reason. Fe plus 2 also good reducing agent. Fe plus 2 also tries to convert into plus 3. It is also a good reducing agent because of it attains a D5 configuration. Response. Both are good reducing agents. But in aqueous medium, this is better reducing agent than iron. Now coming to this. All these points are over. Now, see this point, sir. See here, this point. It is interesting to note that E0 values for manganese, nickel, zinc are more negative than expected. Reason, in case of manganese, configuration is D5. In case of zinc, it is D10. And for nickel, high negative enthalpy of hydration. Same point we have seen here because of D5, here because of D10. In case of nickel, it is enthalpy of hydration. Done or not? Next. An examination for E0 values for redox couple M plus 3 to M plus 2. Just now we have seen M plus 3 to M plus 2 shows that manganese Mn plus 3 and cobalt plus 3 ions are strongest oxidizing agents in aqueous solutions. Right? These values are more positive. The ions Ti plus 2, vanadium plus 2, chromium plus 2 are strong reducing agents and will liberate hydrogen from dilute acids. So I am writing that point. Titanium, vanadium, chromium plus 2. I am writing that point. Titanium plus 2, vanadium plus 2, chromium plus 2. These are all good reducing agents and can liberate H2 from dilute mineral acids. From dilute acids only, they said. So I am writing that. Example they gave. Chromium plus 2 aqueous plus 2H plus aqueous gives rise to 2 chromium plus 3 aqueous, 2 chromium plus 3 aqueous plus H2 gas. Right? Now in chromium +3 state, what is its configuration? In chromium +3 state, what is its configuration? D3. So D3 is stable. D3 is stable because of T2G3. Are you able to understand? Now coming back. These are over. All these things are over. Magnetic properties also over. This table also over. Formation of colors done. Now we are discussing about formation of complex compounds. Next slide reading, sir. Formation of complex compounds. Formation of complex compounds. Online. Are you following?
Yes, sir.
Yes, sir.
Right,
Yes, sir.
sir. No. Smaller the size of central metal, more readily complex formation occurs. And that such complexes are readily stable. Right? For example, if you take S block elements, lithium, sodium, potassium, rubidium, cesium, which can form complexes readily? Lithium. So I'm writing the same. Smaller ions, smaller the size of metal ion, more readily the complex formation occurs. One reason for complex formation is availability of d orbitals high ionic charges, and smaller size of ions. Stop talking. Last bench boys. These three are the reasons for formation of complexes. Can you give examples of complex compounds? Best example. K4, Fe, CN6, potassium hexacyanoferrate. Right? Any other example? I will write K3, Fe, CN6. Here iron is in +2 state. Here iron is in +3 state. Next, nickel tetracarbonyl, NiCO4. Where we have seen this? Mond's process. We discussed this point or not? Mond's process, right? Then FeCO5. Metal carbonides. What is the oxidation state of metals in metal carbonides? 0. Then MnH2O 4 times complex. CuCl4 2 minus complex, etc. All these are examples of complex compounds. Next, sir. Already over. Catalytic properties. What are the two reasons for showing catalytic property? Ability to form variable oxygen states and ability to form complexes. These are the two reasons for catalytic activity. One example we have seen, iron acts as Fe+3 acts as a catalyst during reaction with I- and S2O8 2 minus. Next, formation of interstitial compound. Very, very important, sir. Reason, old JEE advanced question, multiple answer type question. Which among the following statements are correct? Right? In light of formation of interstitial compounds, they gave these 4 options as it is. So answer is ABCD. Are you able to understand? So very, very important. So I'm taking that point. Just a moment. Just a minute. Next heading. Formation of. And what are interstitial compounds? In metal crystal defects. When metals are arranged regularly, there will be some gaps. If a smaller other species, smaller size of other species, if they occupy that gaps, then they are called as interstitial compounds. If a metal ions occupy gaps, we call them as betaloids. They have the formula fractional Fe.930. Correct or not? Right. We also call them as non-stoichiometric compounds. Right? So we are discussing about them. Formation of interstitial compounds. So smaller atoms like yes, nitrogen, carbon, hydrogen, etc. are trapped in crystal lattice, are trapped inside crystal lattice. We call such compounds as non-stoichiometric compounds, or we also call them as betaloids. Such compounds are neither ionic nor covalent. Why they are neither ionic nor covalent? These smaller atoms are trapped. They are not forming any bond. A carbon is trapped inside the crystal lattice. There is no bond between carbon and metal, right? So they are not ionic, not covalent. Example: carbon trapped in titanium, TiC, Mn4n, Fe3H, VH.56, TiH1.7, etc. Properties. So what are the properties of interstitial compounds? 4 properties. 1. They have high melting point and boiling point than pure metals. Point 1. Second point, very hot. Even tougher than diamond, right? Boron nitride is an example. Some borides approach diamond in hardness. Stop talking. Point number 3. They are talking about borides only, right? Boron nitride is harder than diamond. To cut diamonds, we use boron nitride, right? Silicon carbide is also such compound having high abrasive nature, right? Next, they retain metallic conductivity. And I am taking that statements as it is. Fourth point, they are chemically inert. These are the 4 physical properties for interstitial compounds, right? Next, sir. This is over. Next idea, alloy formation. After that, directly compounds, right? KMnO4, K2Cr2O7, silver nitrate. If you discuss these 3, 90% of this chapter, right? So next slide, alloy formation. More than 60% of this chapter is over, sir. Here also, what are alloys? Homogeneous mixture of metals, or we call them as solutions of metals. Or if two metals are mixed uniformly throughout the volume, then we call them as alloys. So alloys are homogeneous solid solutions. Then another important point, if two metals, if I mix to form alloy, their sizes should be approximately same, or their atomic radius difference should not be greater than 15%, right? If the atomic radius difference is greater than 15%, they cannot form alloys. Example, lithium cannot form alloy with potassium, rubidium, cesium, but it can form alloy with sodium. Are you able to understand? Reason, lithium sodium radius difference is not more, but lithium to potassium difference is high. Just a moment, here I need to show this point. Okay, you remind me later, I will have to show that from JDL book, right? I need to open and I have to show that point, right? So I am writing that point here. Alloys are formed by metals. Alloys are formed by metals with metallic radius are in the range of 15% variation. Alloys formed by transition metals are very hard. Example, stainless steel, nickel alloy, right? Chrome steel, and so on. So alloys formed by transition elements are hard and have high melting point. Example, examples of alloys, sir. Very, very famous examples are brass, bronze, right? Brass. S is there, na? So don't use tin or a tin symbol, SN. So don't use S. Bronze, Z is there, na? So don't write zinc. Clear? So brass, alloy of copper, zinc. Bronze, alloy of copper, tin. If I mix both, if I mix these two, then it becomes alloy of copper, zinc, and tin. Then it is called gunmetal. Gunmetal, copper, zinc, tin. Approximately 10% of tin, approximately 2% of zinc, and approximately 80% of copper. Next, bell metal. Bell metal. It is copper and tin. Observe, sir. Bronze, bell metal. Only difference is composition. Then German silver. Old JEE question, sir. Percentage of silver in German silver. How much? 0. It is seems to be like silver, but it is not silver, right? So German silver. It is an alloy of copper, nickel, zinc. Approximately 25 to 30% zinc, 40 to 50% nickel, 25 to 30% copper. Note, very, very, very important point, sir. Note, amalgams are also alloys. Metals on mixing with mercury forms amalgams, which are also alloys. Iron, platinum, tungsten, tantalum, they cannot form amalgams. Next. Invar, steel, invar metal. Yes.
Sir, 1 minute, can you scroll up?
Next. Iron forms different varieties of steel.
Thank you, sir.
On mixing nickel, chromium, tungsten, molybdenum, manganese, etc. Based upon which type of metal is mixed with iron to form steel, that has different properties. Chrome steel, right? For example, alnico. Alnico means aluminum, nickel, cobalt. Alnico, right? As such, we will have different. So we are not bothered about alloys now. In metallurgy chapter, we will write those alloys again. There we will see the list of alloys, right? Next, sir. Alloy formation is over, right? Why we discussed only these things means only those things are mentioned here. Remaining we no need to discuss. Next. What is meant by disproportionation of an oxidation state? It can undergo oxidation as well as reduction. Best example, copper. Copper plus 1 aqueous undergoes disproportionation to form copper plus 2 and copper. Same nonsense here, right? Next, sir. Some important compounds of transition elements in which they are discussing about. All these are different compounds. They are discussing about, see this? V2O5. We discussed this V2O5 under acidic. But what I wrote there, actually it is amphoteric, but its acidic character is that V2O5. However, amphoteric, though mainly acidic. Are you able to understand? So as such, you will find some points. Remaining points also we will see. These things we will study. After that, potassium dichromate, K2Cr2O7. It's a preparation and properties. After that, KMnO4, preparation, properties. After these two, F block. Right? Only two compounds are there in NCERT, but we will see in addition to that another three compounds. Right? ZnSO4, FeSO4, silver nitrate. These three compounds also we will discuss along with these two. After that, we will go to F block. Once if we start F block means almost chapter is over. Right? In F block, only electronic configuration of lanthanides, actinides, general characteristics of lanthanides and actinides. This graph, some reactions of lanthanoids. Right? Same way, electronic configuration of actinoids, ionic sizes, oxidation states. Some comparison between lanthanoids and actinoids. That's all. Applications. Chapter 1. Right? Almost we came to an end. We need to see the compounds. After that, we will discuss the remaining points and we will close it. Right? Today, I will stop the discussion. So in next class, I will start with compounds of D and F block. Right? All right. Tomorrow, listen. First two lectures are chemistry, sir. SR01 students. Morning 8:30 to 11. 11:30. 11:30. Morning 8:30 to 11:30 chemistry class, sir. I will share the link. You join in it. Right? First two lectures are chemistry. Mostly I will try to complete D and F block chapter tomorrow. Right? Listen, one more thing. Coming Wednesday, 5:30 to 8:30, you have class, chemistry class. Coming Wednesday, 5:30 to 8:30, chemistry class. There I will discuss P block. Right? I will not write and so on. I will quickly rush up. Right? It is deleted portion now. Anyhow, we will see it once. Important points of it, right? So mostly this coming Wednesday and next Wednesday also I will take class and I will complete P block. In your regular class, I will start next chapter, coordination components, right? From
Sir.
hereafter, listen, extra syllabus or deleted portions, I will discuss in extra classes only. Are you able to understand? Next, you have surface chemistry chapter, which is deleted portion. If you want to listen to surface chemistry, you need to attend classes on Wednesday, 5:30 to 8. Right? Or you need to attend for weekday also. Then only it is possible. Right? I will end the session, sir.
Sir.
Online only. Online only. Purely online. I will take the class from home. Wednesday. Yes, madam.
Sir, P block is there for this UTS, sir.
D block is there for this UT.
P block and its
B block is also there,
Okay, sir.
but not in detailed way. Whatever we have discussed in periodic classification of elements, now that part of P block is present. Right?
Okay, sir.
Right, madam. Online students, you can leave. I will download your attendance. You can leave.
Sir, 1 minute.
Good night.
Can you show your notes page?
I will post this today's notes now itself.
Okay, sir.
P block also I will post. Yes, Aparajita.
Sir, only on Wednesdays or weekdays as well you'll take?
No. Only on Wednesday.
Online
5:30
or
to
offline?
8:30. Online only. Purely online.
Okay, sir.
Right, madam. Right, sir. Offline, online students, you can leave.
Thank you, sir.